Good afternoon, everyone. It is my pleasure to welcome you at another QSimFP webinar. So this session will be given by Smitha Vishveshwara from University of Illinois. She's a professor of physics at the University of Illinois, and she's a theorist exploring lots of condensed matter phenomena, such as fractionalization of anyons, topological superconductors, non-equilibrium critical dynamics, but also ultracold atomic systems, where she collaborated with different experimental groups to realize quantum condensate bubbles in microgravity conditions, for example, aboard the International Space Station. She also researches parallels between phenomena found in these realms and in gravitational physics, and applies condensed matter concepts to biophysics. She also collaborates and explores the confluence of physics and the arts, and she contributed to many artworks, such as the theater piece Quantum Voyages and the circus performance Cosmic Tumbles and Quantum Leaps. The talk today will be about nano-constrictions and event horizons and the facets of the inverted harmonic oscillator. So without further delay, Smitha, please, the stage is yours.
Thank you so much, Patrick and Silka and Raffaele, for inviting me and for all your warm exchanges. I'm really excited to be here, and I've learned more and more about what you all do, and it's very exciting. I also have to thank Niels Andersen, who proposed having me over to talk in the first place, for that, and also for many special conversations that go back across the decades. So today, what I'd like to tell you about is what we've been studying for almost a decade now, that brings together phenomena starting from the nanoscale in the case of quantum Hall systems and quantum point contacts, all the way up to the astronomical scale of black holes and event horizons. The thing that actually brings this sort of is the glue that looks at common phenomena across all these length scales is the inverted harmonic oscillator. And I'll show you how it manages to weave these different scales together. So we know that there's universal physics across scales, and just to motivate you, for example, when you look at the Higgs-Anderson mechanism that I have on the right here, it's the mechanism by which, when you have spontaneous symmetry broken, this sort of phenomenon could apply equally well to generation of mass in elementary particles. Or if you look at superconductors, the generation of, for example, a London penetration depth and the like, it's the same kind of physics at work in everything from the superconducting mesoscopic scale all the way to elementary particles. Or on the left, if you will, one of the things that's really come into the limelight in quantum materials is the realization of Dirac or Majorana type fermions that, in fact, again, were looked at high energy in the high energy physics realm decades ago. The Kibble-Zurek physics is one more of my favorites, where if you quench across a quantum phase transition, or any phase transition, it could be thermal or it could be quantum, but as you cool a system or change a parameter from a disordered phase to an ordered phase of matter, you could ask what is the non-equilibrium dynamics? How does net order come to be in a non-equilibrium fashion? What kind of excitations are created? And this kind of physics applies equally well to structure formation in the universe in the early stages, or things that you study, vortices in helium as you cool, for example, from a normal phase to a superfluid phase. As Patrick mentioned, I'm a theorist, and I would very much love to hear about how this kind of physics actually gets manifest in experiment. So the thing, of course, is that I don't have to be motivating this to the audience here. I'm really excited to look at the kinds of things that you've been exploring, things, for example, that Silka was telling me with her group right now, fluid flow, looking at analogs of black holes and the like. Very exciting and very much in keeping with the kinds of things that I'll share with you today. And of course, I don't know, Patrick, you can tell me what the format is. Should I take questions along the way, or should I first give my talk and then take questions at the end?
Yeah, I think you can proceed and save the question for the end.
Okay, perfect. I'll do that. Okay, so first off, oftentimes it so happens that when one is looking at this kind of common phenomenon across scales, oftentimes there's some kind of simple model at work. And so, for example, the one that we know and love, the simple harmonic oscillator, this could apply to a whole wide range of systems. When you look at, for example, particles trapped in potentials, these could be ultracold atoms, or nanomechanics when you're looking at oscillations about equilibrium, phonons, plasmons, any sort of excitation, if you will, you have some kind of equilibrium, you're looking at slight deviations away from equilibrium, and then in the quantum version, voila, you have the quantum harmonic oscillator. So this is something that we know and we love. The quantum Hall system, which I'll tell you about, is also a prime example of that. And as a theorist, oftentimes I'm trying to see if, no matter how complicated some kind of strongly correlated system is, I'm always trying to get it down to the physics of a harmonic oscillator. And once that happens, one is in business. At least for those of us that are sitting and doing analytic calculations. Well, the protagonist for today is its sister system, the inverted harmonic oscillator. So it's just like the simple harmonic oscillator, but facing downwards. And this too, it's the lesser known sister compared to the simple harmonic oscillator, but it too has a venerable history going back several decades. If you look at the quantum version, for example, in the case of nuclear decay, you're really looking at tunneling across some kind of potential maximum. And that, once again, it's the inverted harmonic oscillator that's at work.
I think Smitha just broke off with the connection. Can someone hear Smitha actually?
This talk, three very diverse systems. The first one will be the quantum Hall system. And again, because these are all three very different systems, I'm not going to give a very technical sort of technical description. I will try to go over the basics for each of the different systems. So in the quantum Hall system, you'll see that in the presence of what's called a point contact, so it's this little thing, this is the quantum Hall system, and here, when you have the two edges squeezed together, you have a point contact here. And you find that, again, in this realm, it's the inverted harmonic oscillator that's at work. The same kind of physics that you have in the quantum Hall system and in the presence of the quantum point contact, one finds that there are some beautiful analogies with quantum optics. And finally, the same physics, or the same kind of key inverted harmonic physics, oscillator physics, also plays a role in the black hole realm. And so what are the connecting links? We'll see that if you look at the parallels between the quantum Hall system and quantum optics, there's a one-to-one correspondence between what are called coherent states that apply equally well in the quantum Hall realm as well as in the quantum optics realm. And then if you look at squeezing in quantum optics, a well-known phenomenon, it has its parallel with the quantum Hall point contact. And again, at the heart of it is the inverted harmonic oscillator. Between the quantum Hall point contact and black holes, you might wonder, is there any sort of parallel at all? One of the things that we've been really excited in exploring is, in fact, the parallels that are at work between these two systems. And what I will show you in the second part of my talk is that there's a very strong parallel between tunneling across the quantum Hall point contact. And actually, let's see if, there's a little bar here I can't actually see everything. Okay, there we go. And there's actually a very close parallel between tunneling across the quantum Hall point contact and Hawking-Unruh radiation. And then there's also an analog between a kind of ring down that you can have, a little jolt that you can give in the quantum Hall scenario, and the analogous phenomenon in black hole physics, ring down, if you will, or what are known as quasi-normal modes. I should say that it's particularly special to be giving this talk to this group here for multiple reasons. One is the fact that Professor Unruh is, in fact, associated with your group, so it makes it really, really special. And then the connection that I have with Niels is that my father was a black hole physicist, C.V. Vishveshwara, and our connections go back far across decades through my father. And he was, in fact, one of the people that pioneered the prediction of quasi-normal modes in the black hole setting. So if you're interested, here are a couple of references. And who are the people that I've been working with? There's several of them, but the primary work that I'll present here was performed by two of my former students, Varsha Subramanian and Suraj Hegde, along with my colleague, Barry Bradlin. So the works that I refer to, it's really, these are the three people, these are the three key collaborators. But this work also has its history. It's been built on over about, by now it's 20 years, I think, that it's been building up. And Mike Stone and Deeptiman Sen, they're the ones who really worked with me on the quantum Hall basics. Nigel Cooper is another person where we looked at things like the squeeze states and what I told you about. And my father, C.V. Vishveshwara, while he's no longer alive, he's had a lifelong influence. And that's why it's been very natural for me to bring together condensed matter, cold atomic physics, quantum optics, and look at the parallels with gravitational physics and black holes. Okay, so now let's actually dive into this journey here. And in the remaining half hour I have or so, this is what I will walk you through. First, I will tell you a little bit about the quantum Hall system, the basics. How do you model the point contact? And I will show you that in particular, it's very natural when you have the quantum Hall system to look at a saddle potential, which models for you this the point contact, and that in turn gives you tunneling, the phenomenon of tunneling that I mentioned. Then what I'll do for you is I will show you where the parallels lie with quantum optics. Almost immediately, the moment I lay out the basics of the quantum Hall system for you, we'll be able to identify what the parallels are with coherent states, with squeezing. It naturally emerges from the language that I'll present to you. And finally, I'll show you where the black hole dynamics lies, and you'll see exactly where the parallels come in with Hawking-Unruh radiation and quasi-normal modes. And in particular, I will show you that tunneling in the quantum Hall system, squeezing in the quantum optics system, and Hawking-Unruh radiation in the event horizon or black hole setting have an exact parallel. And I will, at the very end, show you what are the lessons that one learns by looking at parallels? Can you make predictions in one realm by borrowing from the other realm? Can you go back and forth between these realms? These are the kinds of things that I will address at the end, and I'll show you that there's some rather lovely predictions that one is able to make. All right, so now the quantum Hall system. This is a two-dimensional system, a two-dimensional electron gas subject to a very high magnetic field. And when one starts cooling down in temperature, one starts seeing quantum effects coming into play. One sees the dance of highly correlated electronic phenomena. And in fact, what one sees is that one of the reasons that the quantum Hall system is so celebrated is that when you apply a magnetic field, then you see that you generate, if there's a current passing through, you generate a transverse voltage. And so if you look at the ratio between the current and the voltage, that gives you the Hall conductance. And the beauty of this system is that Hall conductance is quantized in units of a combination of universal constants, E squared, E the electronic charge, and H Planck's constant. And this really has, in a sense, hidden in it a topological kind of nature to it that renders this universal Hall conductance robust. So now what happens is that when you look at the different states that emerge, they emerge in different fractions of E squared over H. They could be integer, that would be the integer quantum Hall effect. And then, but if you look at fractions, you find that those are much more complicated states of matter with very exciting ground states that are truly quantum many-body. One of the beautiful things that emerges that I'll barely have a chance to talk about is that when you look at the emergent excitations of these systems, they can be fractional. So they can possess a fraction of the electron's charge. Not only that, these particles can have extremely interesting quantum statistics. They don't have to be fermions, or they don't have to be bosons. Upon exchange, instead of just picking up a -1 for fermions or just remaining unchanged for bosons, they can pick up a fractional phase. So these are anyons, so to speak. I'll only mention this in passing. What's been very exciting in the field is that experimentally, the developments have been tremendous for the past 40 years. And you can really have beautifully patterned systems. You can do all kinds of things to this. So here in the quantum point contact, what you have is that the current is carried by the edge. The gap is bulk. The bulk is gapped. And so if you look at the physics, it's usually taking place along the edges. But you can do all kinds of things with the edges using gates and the like. You can bring them together. You can look in tunneling between the edge states. And through these kinds of measurements and magic, people have actually shown that the things that tunnel across have fractional charge. And in the last 4 years, there's been a huge development in showing that these particles not only have fractional charge, they also have fractional statistics. And so what's been very exciting in our field is that people have actually detected or observed fractional particles that are anyons. Okay, so this is a little bit of background with the quantum Hall system. And now let me just look at it very simply and boil it down to the essence. So if you look at the physics of this, it's really, if we're just looking at the single particle version, it's a particle in 2 dimensions subject to a transverse magnetic field. So I just have the Hamiltonian written here. And if I look at a symmetric gauge for the magnetic field, this is what I have here. So now solving for this ends up being quite a simple problem. And the way you would go about it is you would find 2 appropriate conjugate set of variables. And then you actually find that this 2-dimensional system just maps to a 1D simple harmonic oscillator. And so now you know that with the simple harmonic oscillator, the levels are quantized and evenly spaced. And so what ends up happening is that these levels are what are called Landau levels, and they're separated by h bar omega c, where omega c is the cyclotron frequency. So now, so what's happened here is you've taken the two-dimensional problem and you've mapped it onto a one-dimensional simple harmonic oscillator. So then you could say, where has that other degree of freedom gone? Where it's gone in is that if you look at each of these 1D harmonic oscillator levels, within each level, you have an extremely degenerate ground state where you have many, many, many states. So it's an infinitely degenerate set of states in each of these Landau levels, so to speak. And if you look at the lowest Landau level, that's where all the physics takes place. That's where all the action takes place. And you have this infinite degeneracy. And by the way, for those of you that are not very interested in all the technical details, as I keep going, just feel free to nap a little bit. I will keep changing topics and I will keep trying to emphasize the essence that comes out of each of these topics. So if you want to gloss over any of the technical parts, please feel free to do so, and I will summarize at each of these different sections. Okay, we're not going to go over exactly how to solve this problem, but I already told you there are these two sets of conjugate variables, and you can map this on to a simple harmonic oscillator. If anybody is interested in the exact details, it's quite a cute problem to solve. Okay, now when you look at the lowest Landau level, as I told you, this thing is infinitely degenerate. So if I look purely at the ground state, there's a whole other set of states. They can be characterized by angular momentum. So if I see down here, Patrick, I have a question for you. Can you see my pointer when I move this around?
Yeah, we can see it well.
Okay, perfect. Okay, so you actually have this, for example, if you look at the ground state, what it really is in the symmetric gauge, it consists of circles, concentric circles at different radii, and each of these circles carries different units of angular momentum. Okay, then the next thing that's very interesting is if you're just looking at the lowest Landau level, which is the one that's of interest here, then it turns out that because you've projected onto the lowest Landau level, X and Y don't commute. So what happens is in the lowest Landau level, if you look at any particle, or I will say quasi-particle, any natural excitation of the system, it's sort of going around in tiny circles because there's a very high magnetic field. And if you follow its drift, it does so in an extremely weird space where X and Y themselves don't commute. And that's because you've thrown away all these sort of small length degrees of freedom. So this is important. X and Y do not commute. Okay, so now this actually brings me immediately to the parallels with quantum optics. So now we live in the quantum Hall system in the lowest Landau level. We're living in this very strange space where X and Y do not commute. And now you can compare it to phase space, for example, with any quantum system, or you could look at photons in some kind of particular quantum optics system. And what's interesting here is just the way in the quantum Hall system, X and Y do not commute, we're more familiar with quantum optics where position and momentum do not commute. This is basic quantum physics. X and P do not commute. So if you go back to your basic quantum physics and say, let me just think of phase space, let me think of X and P, where these don't commute. And I can map the same kind of picture onto the lowest Landau level, except this is real space. This is X and Y, while in the optics case, or, you know, in just a particle in some quantum potential case, you have X and P. So that's going to be phase space. And in the quantum Hall system, you have real space. Okay, so what can we do now? One of the things you can show is that in phase space, because X and P do not commute, we all know that there's some kind of Heisenberg's uncertainty. We know that we cannot completely localize position and momentum. So any quantum object, any photon, that would have some kind of spread in position and in momentum, and the product of those two would respect Heisenberg's uncertainty principle. Likewise, in the quantum Hall system, we have, let me go back to this. We have the same kind of principle going on, except instead of Planck's constant h bar, you actually have the magnetic length. So the magnetic length plays the role of Planck's constant. The smallest particle that you can have is the size of the magnetic length. So now, for those of you that are interested and familiar with coherent states, these are the states that respect this kind of minimum uncertainty. And the way you can do this is in quantum optics, it's actually a wave packet composed of states of different number, 1 photon, 2 photons, 3 photons, etc. If you pick a particular linear combination, you can create this coherent state that respects this minimum uncertainty. Likewise, never mind the details, in the quantum Hall system, you can create a wave packet that respects minimum uncertainty, but now what it does is it actually is composed of these different angular momentum states. So it's not photon number. In the photonic case, it's different photon number. In the lowest Landau level, it's different angular momenta. Okay, excellent. So now we have the basics in play. And now we can say, what can we do with this kind of thing? How in the lowest Landau level, because all these states are degenerate, there's no movement, there's no time evolution. So now we're ready. We have the basics and we can say, what's going to be the next step of this game? How can we move these particles around? So this is when I come to the nano-constrictions in the quantum Hall system. And so now let me go back to the physics of this point contact geometry. And I can tell you one thing. So if you look at the actual quantum Hall system, what I told you was the bulk. It was just this extended 2D system. But in reality, there's lots of other things happening. For example, the edges could come close together. You could have disorder. You could have some kind of very complicated landscape. And so now you could say, what is the simplest kind of potential that I can apply in this lowest Landau level? And so it turns out that the simplest potential that you can apply is a saddle potential. And if you look at the heart of this point contact, you actually have a saddle potential that's sitting there. So the saddle potential is just, here are examples of the saddle potential, u times x, y, or y squared minus x squared, if you will. And so then if you look at the equipotential lines of these saddle potentials, they're like what I showed you here. It's a sort of hyperbolic shape that you have. And here are the saddle potential lines. Okay, now if you look at this saddle potential, there's lots of parallels with quantum optics. So for example, in quantum optics or beam splitter, what you can have is you can have an incoming particle and it can either reflect off and go off in one direction or transmit. So there's an incoming particle that can either get reflected and go into one detector here, or it can get transmitted. The same kind of thing can happen to the saddle. You can have an incoming particle that either goes off this way, or it may tunnel and go to the other side. So there are all kinds of parallels with quantum optics, but there's an even stronger parallel, which I'll talk about in just a second, and that has to do with squeezing. So now, when we look at this saddle potential in a little bit closer, you can see it's exactly as I told you. You have two incoming directions and two outgoing directions. So you can have an incident wave that's either reflected or transmitted. That's what happens in this saddle potential. Interestingly, when you actually write the outgoing states in terms of the incoming states, for those of you that are familiar with Bogoliubov transforms, be it in superfluids, be it in relativity, you have exactly the same kind of structure here. So you have, if you look at the incoming states and then say, how are they related to the outgoing states? They're related through Bogoliubov transforms. And this is going to end up being quite important. Okay, one last thing that I'll tell you about is that I told you, if you remember, that X and Y don't commute. So in a way, if you look at Y, it plays the role of momentum, P. Y and P are similar. And so in fact, if you use that parallel, you find that this maps on to a one-dimensional system that looks like so, and you see that Y plays the role of momentum, and what kind of potential you have sitting here is exactly an inverted harmonic oscillator. Oh.
I think we might have some connection problems again.
And now we've introduced the saddle potential. We've also introduced the inverted. Yeah, sorry.
You broke off for maybe 15 or 20 seconds, and also it's 20 minutes from the end of the seminar. So if you can repeat your slide.
Okay. So the last thing that I said is now what we're focusing on is the physics of the inverted harmonic oscillator. And so let me go through some of the properties, and then in the next two slides, I'm going to show you what the dynamics looks like of these coherent states. And then I'm going to introduce to you the parallel with black holes. Okay, so one thing to note is we already talked about the incoming and outgoing states. These are the scattering states of an inverted harmonic oscillator, and it's extremely general. Anytime you have some kind of potential barrier, anytime you have some kind of potential maximum, these are the kind of natural states that come into play. These are the scattering states. In addition, you find that there are some extremely interesting states that don't have a parallel with their sister harmonic oscillator system. And these are ones that have imaginary eigenvalues. And so these actually correspond to decaying modes. And so they correspond to modes which can actually just decay in time. And so that's going to be another part of the spectrum. These are related to the quasi-normal modes. Okay, so now very briefly, because I don't have time to go into the details, let me just, we're not even going to look at all the details of the time evolution and the like. Those of you that are familiar with quantum optics, you'll immediately recognize that this saddle potential acts as a squeezing operator. So what it really does is if you have a coherent state that is symmetric, as you time evolve under the squeezing operator, it makes this coherent state skinny in one direction, so it minimizes the uncertainty in one direction, but the payoff is that it extends it in the other direction. So never mind the math, but you can actually see here's a coherent state. And when there's a squeezing operator, what it does is it squeezes it in a particular direction. It turns out that with the quantum Hall system, what it does is that it also time evolves along these equipotential lines. So what you really have is this coherent state, and as you apply the saddle potential, it tends to go along an equipotential line and get skinnier and skinnier. So now there's actually beautiful physics associated with this, and you can say, what happens, how is the actual dynamic evolution and the like. Can you evolve two particles? You can do all this, and you can show that it acts exactly like a beam splitter. There can be an incoming particle that goes off in one direction, but you can also have quantum tunneling onto the other segment of the saddle. And that's exactly how you have quantum tunneling through your quantum point contact. I don't have a chance to talk about two particles, but you could also have two particles, and you could say, do they go off in the same direction, or do they go off in the opposite direction, or opposite directions? Let me just make a comment that this is the sort of key that has a key principle that's been used to look at quantum statistics. If you look at the proposals that several of us have had for about 2 decades, and the experiments that were done 4 years ago, they followed these kind of principles. And so you can actually tell, are these fermions, are these bosons, are these anyons? It really, you can make measurements where, depending on whether these are friendly particles or unfriendly particles, they tend to go off either along the same limb as bosons would do, or in opposite limbs as fermions would do. If there are any questions in the little time that I'll have left, I will answer those questions. Okay, so this is just to say that these things were observed. So now let me come to the last part, which is the analogy with black holes. If you look at this here, if you look at sort of the time evolution of this particle along these equipotential lines, there's something really interesting. Unless there was some sort of quantum process, anything that was on the bottom half of the saddle remains on that side. There's no way for it to come out to the opposite side of the saddle, to the upper half of the saddle, unless there's actually tunneling across. And so in some sense, one could very glibly say, oh, that looks like some kind of event horizon. It turns out that it's more than just in passing. There's a very, very strong parallel between what I set up for you here in the past half hour and the physics of black holes, relativity, and the like. So in the 10 minutes that I have, I will breeze through what the parallels are, and then during the question time, I can answer that very briefly as well. I'm sorry, we started a little bit late, so I didn't time this well enough. So I'm sorry that there's only 10 minutes of black holes, but I hope this is the beginning of a longer conversation. So very briefly, let me just say that there's a lovely parallel between this saddle potential time evolution and the sort of, if you're now looking at general relativity and you're looking at the time evolution in different accelerating frames, then if you look at space-time, there's something called Ringler coordinates that, of course, and those of you that do relativity, you will be teaching me more details. But if you look at the way you have an accelerating observer, and you look at the time evolution, it's exactly the same as the time evolution that I showed you in the saddle potential dynamics, except that instead of X and Y here, in the relativity case, you have X and T. And there's an associated Rindler Hamiltonian, and it's exactly the same kind of time evolution as what I showed you with the saddle potential. More so, if you now look, you have the Unruh effect, which again, what is the Unruh effect? And I don't know if he's here. I will one day happily learn from Professor Unruh himself. But essentially, the idea here is if you look at any kind of field that you might have, and it's in a vacuum for the inertial observer, you find that it acts as a thermal bath for the accelerating observer. And there's many different ways of understanding it. I had to understand it first through cartoons and kind of see what is the coordinate transformation that happens between these different observers. But you can sit down and actually make these coordinate transformations, and you can show yourself that if you look at Minkowski space or an inertial observer, and then compare what happens in an accelerating frame, you actually do get a thermal bath. And now this is, of course, also related to what happens at the surface of a black hole, and that is related to Hawking radiation. So it turns out that if you look very briefly, and this is what you can ask me questions on as we go further, I told you that there is tunneling happening across the saddle in the quantum Hall system. And there's some kind of tunneling matrix element to go from one side of the saddle to the other. It turns out that, again, this is the physics of Bogoliubov transforms. And if you compare this with Hawking radiation across an event horizon, there's a one-to-one formal correspondence between these two systems. The strength of the saddle, it turns out, is related to the Hawking temperature. So this is just one parallel that arises, and there's actually a very physical way of looking at this. And I'm happy to tell you more about this when we ask questions. And finally, the last part of the black hole analogy and this whole presentation that I have, I told you right at the start that there were two aspects to the inverted harmonic oscillator. One is looking at these tunneling and the tunneling between incoming and the outgoing. And I told you very quickly that it has an exact parallel with Hawking Unruh radiation. But I'd also told you that there are these other modes, these decaying modes, these quasi-normal modes that are intrinsic to the inverted harmonic oscillator system. And so that brings me to the last part of the black hole parallel, and that has to do with ring downs. Never mind what the mathematical structure is. It's very rich. It appears as a pole in the scattering matrix. If you're interested, there's beautiful math behind it. But of course, physically, it's something that has been studied more and more, starting with the first gravitational wave detection, starting at the sort of signal that was shown, this ring down signal, if you will. And just as a personal story, I told you my father was a black hole physicist. He passed away in 2017. He had dreamed about this detection, the detection of gravitational waves all his life. He'd also hoped that there'd be hints of these quasi-normal modes. And the part of the story is that he did actually live to see this, and he was in good health when the first detection was announced. So just to tell you very briefly in one word what he did in his treatment, the one that I learned just in passing, he would tell me when I was a kid that it's kind of like hearing the gong of a bell when you strike it, except it's very hard to strike a black hole. And these are not sound waves, but they're these space-time waves, if you will. They're gravitational waves, but it's that same kind of gong-like sound. Of course, in future years, in later years, actually only in the last 10 years, I found out how he worked it through in the 1970s. And voila, what you really have is, if you're looking outside, this is, for example, a Schwarzschild, no, this is a Schwarzschild black hole. And if you look at this, if you look at, for example, the metric and scattering off of that, you find that there is a potential maximum outside the event horizon. And it's really the ring down or the sort of decaying modes that are coming from, you can essentially boil it down to that maximum in the potential that you have. So in the last minute that I have, let me put all these things together. So in the black hole situation, apart from Hawking under radiation, you also have ring down. You need something cataclysmic, like the merger of two black holes, to actually excite this ring down, but it is the natural mode that exists in the black hole. And what is the characteristic feature? It's that inverted harmonic oscillator that's really sitting there. It's a scattering off of that that's giving you this ring down. Let's go back to where we started. We started with tunneling across the saddle. And hopefully I've convinced you by now that the key physics, I'm almost done, the key physics there is also the inverted harmonic oscillator. And so this is something that we absolutely hadn't foreseen at all, but based on the universality of the inverted harmonic oscillator and its associated physics, given that the black hole case has this decaying mode, there should be one also in this point contact. And so that's really the prediction. That's a sort of new prediction that we've proposed. If you send in a pulse of electric charge in the quantum point contact geometry, you should see a ring down, which is very akin to what is characteristic of black holes. Of course, the time scales and length scales are absolutely different. One solar mass black hole, and then you have a typical time scale of 0.35 milliseconds, which, by the way, I find incredibly mind-blowing. And now if you look in the nanoscale realm, you actually find that you have nanosecond ring down frequencies, which can actually be measured. And so these are some of the things that we've been playing with. I see that I've run out of time, but hopefully I've given you a taste of the very rich physics that exists through these commonalities, bringing together phenomena from the nanoscale quantum Hall system, the quantum optics, to the astronomical scale of black holes. And with that, let me thank you all. Well, here's a brief summary. Once again, it looks like a little cat that's winking, but this is the summary that I have here. And thank you all so much for being here with me today.